Hello guys, let's solve flatten nested list iterator today. So in this question we are given a nested list of integers called nested list where each element can either be an integer or a list itself. And again, the list can contain elements which are again integers or lists and so on. So in this question we basically need to implement this class, and that means we need to define the constructor, the next method, and the has next method. So the next method basically returns the next value in the iterator, and the has next method returns a bool indicating whether do we still have more elements left in the iterator or not, right? And our code will be tested with this sort of a pseudocode where you see they use our has next method to check if we still have elements to cover. If yes, we append the next element by calling the next method, and then we finally return the list. So let's quickly walk through an example. So if this is the given input, we see how the elements are retrieved one by one using the next method, and finally a list of all the elements are returned. And note that it should be in the same order, right? And one more thing about this question is we are given an interface called nested integer. So this nested list is actually a list of nested integers. So this interface basically makes our job easier. We've defined 3 utility methods that we can reuse for our algorithm. So the first method is an isInteger method that basically returns true if the item is an integer or not. The item is an integer. The second method you can use to get the integer value of an item if it's an integer. And the third method is a getList method, which basically returns a list of nested integers, right? So let's see how to solve this problem. So I'll be solving this problem in 3 different methods. One with a recursive approach, 2 an iterative approach using stacks, and in the third method I'll show how to use generators as well. Yeah, so let's see how to solve this. Alright, so in the first method we'll be using a pretty naive approach where we'll try to completely flatten the list in the constructor itself, and once we have the flattened list here, the next and the has next methods can be implemented pretty easily. So let's see how to do that. So let's have a list called flattened list, which will basically store our final list, flattened list, and we'll be using a recursive approach to do this. So let's say we have recurs item, and if item is an integer. So remember how I was talking about the interface where we can reuse these methods. So if the item is an integer, what we do is we directly append it to the flattened list. Append, and you can get the integer value using the method getInteger, right? You can go ahead and return. So if this is not an integer, that means that this item is again another list. So what we need to do is basically loop over the list. So we can call it for inner item in. We can get the list using the getList method. For inner item and item.getList, we just need to call recurse of inner item, right? So this is a pretty easy way to flatten a given list. So let's test this out. Note that the input to the problem is actually a list of nested integers. This is pretty stupid actually. We could have directly given it as a nested integer, because that is again can be a list or an integer. That could have made the problem a bit more elegant, but since it's a normal list of nested integers, we need to do one loop. We need to loop over each item of nested list and call our recursive function, right? So once we call our recursive function, the flatten list variable will be populated, and that would contain a flatten list, and then the problem is pretty easy to solve. So let's just use a class variable called index to keep track of what index we are currently at. So to implement the next method, you can just return the element at index, and then make sure you increment index by 1, and then you finally return result, right? And has next can also be easily implemented as like basically if index is within the bounds, that means has next has to be true. So you can return true if self dot index is lesser than the length of the flattened list. And return false. So that should be the code for this method. Let's see if it works. Yeah, there should be self dot index. Okay, that works. Yeah, this seems to work. So if you notice, what do you think is a problem for this method? Like if you see here, we are doing the entire flattening in the constructor itself, which means the space complexity is going to be O of n plus whatever space the recursion is using. So let's call it L. So it's going to be O of n plus L. But the other two methods are pretty fast. So these two methods are going to be O of 1. So let's see if we can do slightly better. Yeah, so in this method, we'll be using stacks to solve the same problem. So the idea is to sort of iteratively unpack the stack and one by one add elements to the flattened list. So if you think about it, recursion is also internally implemented as a stack. So that gives you an intuition as to why this method actually works. So let's first initialize the stack with the given list. So let's say this is a given input. So note that this input has 3 elements, 0, 1, 2, where the first element is this huge list and the next 2 elements are integers, right? So let's initialize the stack with the given list, but every time we add elements to the stack, we're going to reverse it and add it. So the reason for doing that is because stacks are implemented as FIFO, which means first in, first out. So whenever we pop the stack, we need this element first, right? So that's the reason why we always reverse it. So it's going to be initialized with this list 4, 5, 6, 6, right? Yeah, so this is going to be the initial state of the stack. Now what we're going to do is we're going to pop the stack and we're going to check if it is an integer or a list. If it is an integer, that means we can directly return it. So this is the implementation of the next method. So here we have, so this is the this is the element that will be popped, and if it is an integer, we can directly return it. So you can imagine as to why that works, because if this is an integer, that should be, if this is an integer, that should be the first value that's actually being returned, right? So we'll do that check first. If it is not an integer, we're going to try and iteratively unpack the element. So that is the case here. So the first step is to pop it. So once you pop it, we're going to extend the stack by unpacking this list. So like I said before, while unpacking this list, we're going to again reverse the list and add it back to the stack. So the reversed elements are going to look like 5, 6, 6, 4, 1, 2, 3. So this is the stack state in the second step, and we're going to repeat the same thing again. We're going to pop the last element and then reverse it and extend the stack. So the stack is going to look like 4, 3, 2, 1. Now the last element of the stack, we're going to pop it, and we see that it's an integer directly, so we can go ahead and return it, right? And the next time next is called, we we can pop it and return the value, and so on. And pop it and return the values 1, 2, 3, 4. And then once we come here, we will again repeat the same process. We'll have to pop it, and the next stack state is going to look like 8, 7, 6, 5, right? And then during the next call, we pop this and append 5 to the list, and so on. So you see how this method works. And for the has next method, that is pretty straightforward, because since we have a stack variable, whenever the stack variable actually has elements in it, that means that has next needs to return true. If not, it needs to return false, right? Well, let's see how to code this. So let's start coding this approach. So let me initialize the stack here. And like I said, every time I add elements to the stack, I'm always gonna reverse it. So in Python, you can easily reverse a given list this way. And that's all we need to do in the constructor. And in the next method, what we're gonna do is we'll be first doing the unpacking, right? So let's write a loop. So while there are elements actually there in the stack, and we need to make sure that the top of the stack is not an integer. If it is an integer, we can directly return it. So while the top of the stack is not an integer, we need to sort of unpack that unpack the top of the stack and add it back to the stack. So that we can basically do it as self.stack.extend. So extend by what? Extend by the element that is being popped, right? So you can go ahead and call pop. So once we call pop, we now have the top of the stack, and that needs to be reversed. And note that all these items are of type nested integer. So to get the actual list, we need to call get list, and we are going to reverse this, which we can again use the same method, right? So at the end of the loop, we can make sure that the top of the stack will be an integer, right? Which we can now again pop it and return it. So we're going to say stack.pop. So we have the top of the stack, and we can call get integer on it, right? And for the has next method, like I said, all we need to do is just return if stack has elements in it, right? If the length of stack is greater than 0, it'll return true. If not, it's going to return false. But the problem with this approach is that, so let's say the stack is, the stack is in this state. So in that case, the length of stack is going to be 1 because it has an empty list inside, right? But technically this is an empty stack. So how do we solve this? So the idea is to basically do the same thing again, right? So once we do an unpack, the stack from this state will go to this state, and that's what we want. And then we can again use the same logic. So what I'm going to do is actually just take this part and put it into a utility function called unpack. So unpack is basically going to take the stack and make sure that the top of the stack is not a list. So that's the job of unpack. Every time unpack is called, it's going to take the current stack and it will make sure that the top of the stack is not an integer. If it is an integer, it's going to do a level of unpacking by doing the pop and reversing as we discussed. So here we just need to call unpack. Similarly, we just need to call unpack here and there. Right? And that's about it. Should work. Yes, it works. Cool. Now, in the last approach, we're going to use something called generators. So to give a quick overview of what generators are, for example, the range function in Python, that is actually a generator. So how it works is the idea is that anybody can actually write a generator function this way. So let's say we want to write a range function. So idea is that we run a loop, and every time we need to return a value, instead of returning it, we yield. So by yielding, what we're saying is the function state is sort of temporarily paused, so that the next time the generator is called again with the next keyword, the function state sort of resumes. That way, so that's the difference between doing a return and a yield. The return is a hard stop. The entire function is executed and then you do a return. But if you have a loop and you do a yield, that means that you're going to sort of temporarily pause the loop, yield, and then resume from the same state. So let's see how to do that. So let's start coding this approach. First, let's define our generator object. So we'll be writing this function called nested generator. That's going to take our nested list into as an input, and we'll also have a variable called return val. I'll explain why this is needed. We can set to none. Right? Now let's first define our generator function. So this basically takes in a list as an input, and so what we're going to do here is basically loop over each element of the list, and we're going to check if this item is an integer, which we can now do as is integer. So if it is an integer, what we're going to do is return it, right? Return item dot get integer. So this is where the idea of generator comes into play. So if we do a return, that means this loop sort of stops abruptly. We don't want that. We want to remember this particular state. So we need to do a yield, right? And in the other case, where item is not an integer, that means that item is a list. In that case, what do we need to do? Basically recursively call our generator with item as an argument. So what we will do is, rather than returning item, we are going to recursively call this generator as generator with item. And remember that since item is a list, we need to call get list to get the actual list. And in Python, whenever you do a recursion, a recursive call on a generator, it's not correct if you do just the yield, but rather you need to say yield from. So that's the Pythonic way to do it. So I would strongly suggest you to read more about generators if you're interested. So so that you get a better understanding, right? So this is our generator, which we have now initialized into this variable. Now let's implement our next function. So the idea is that the next function will always return whatever value stored in the return val, right? Now let's see how this return val is actually getting populated. So that happens in hasNext. Okay, so if you see the pseudocode, they're gonna call hasNext first. So they're making sure if does it have another variable, another element to be returned. In that case, you call next and return the value, right? So hasNext is always called first. So whenever hasNext is called, you can set the return value by calling the next on the generator. So this is how generators actually work. So every time a next is called on a generator object, one value is yielded, and the function state is sort of paused at that particular state, and the next time next is called on the generator, it sort of resumes. So if you think about it, this method is literally exactly the same method as our first approach, but rather than having a recursive method that populates the flattened list and then do the iterating over the flattened list, we are utilizing the concept of generators to do all that for us, right? So now how do we return false here? So how do we know that there are no more items to be returned from the generator? So this can be done using a try-catch sort of code block. So in Python, whenever a generator is done, like let's say we have iterated among all the items in generator and we try to call next again. So in that case, Python, what it does is it returns a stop exception. So we can use that as a signal to indicate that our iterator is done, right? So if we'll put this inside a try block, so if this succeeds, we can say we do have an element and so return true. If not, we can catch the exception and say return false, right? So every time hasNext is called, we're going to try calling next on the generator and store it in return value. So it's going to return true, and the next time next is called, we know what value to return, and this is going to keep going on and on and on, and at one point this is going to raise a stop exception. In that case, false will be returned, right? And this generator is the core logic of this approach. Now let's see what's the advantage of using this method. So let's think about the time and space complexity for this approach. So as you see here, the constructor is just O of 1, because all you do is just initialize an instance of the generator. Next is again O of 1, hasNext is again O of 1. But the space complexity is going to be O of D, where D represents the sort of the recursion depth. Since we do like a recursive call to the generator, the recursion stack is going to take some space. So that's the only space that this approach actually uses. So that's about it for this approach and this problem as well. I felt that this was a pretty cool problem to solve. It's a good design question, as it has the potential to test a lot of good concepts like iterators, generators, recursion, and so on. So yeah, thank you for watching.